Okay, so I think that is, yep, that looks like it's going. So let's get started. So maps. I'm not sure how. Okay, yeah. All right, so we're good to go. All right, so maps. Um, basically, map is a searchable collection of key value items. So we've talked about key value items before, um, in terms of the heap, and the heap basically was a priority heap. If you'll remember from last time, where we had this idea of key value entries into a heap. So, you know, this is very similar. Um, it's just that in a heap, basically, you can have a priority heap like we talked about, but a map inserts more structure on top of it. So that's really the difference in these ADTs is that with a map you have more operations and more behavioral definitions such as searching and inserting and deleting items. Excuse me. So in a map you have searching, you have insertion, you have deletion. Um, Now in a map also, which is different from a multi-map, you'll see that you do not have multiple entries allowed in a map. That's what a multi-map is for. And by the way, a lot of this stuff is uh, is in the STL in C++ as well as various Java libraries, and we'll talk about those as well this week. So there's a lot of applications for this. You can use it for an address book. You can use it for student records, employees, customers. You could have a lot of people will have like ID numbers tied to the actual records, or they might have names tied to the IDs, or it's basically if you think about it, really it's a way to keep track of this data and bind two things together. So binding a key to a value, and in that sense, maps are extremely useful. Now the extra structure that I talked about is here. That the fact that a map has these things means that it's sort of a more full-featured data structure than like the priority heap we looked at. You've got get, put, remove, size, entry set, key set, values. So all of these are various things that can be done to the map. The get assumes that you have a key already, and if you do have that key, it returns the associated value. So let's say, for example, like we use our phone book example, if we have a name, we can get a phone number. So, we'd look up the name in the phone book. Not that people really use phone books much anymore, but um, you know, bringing it a little more modern. I mean, it's just, in that sense, it's similar to like a URL, right? I mean, if you type in a URL, that's the key basically. But what is the value? Well, the value is the index.html page or the index.htm page or whatever the server is serving up, whether it's with ASP or with PHP or whatever. That's the content is the value. The value is the content, and the key is just the HTML address that's being used. So there's a lot of different analogies in computer science of what that key could be. Now, when you do a put K and V, that's where you're actually taking the value of the content that you want to store, and you're sticking it into the map using a certain key. Um, so important to note here is that if it's not already in M, it'll return null. Otherwise, the standard map ADT definition is to just return the old value that was associated with it. So if you had already inserted something into that position, you would just get back the previously inserted um, value. And then you can do a remove, which just removes the entry from the map. I wonder if, let's see here. I'm going to try to do video. If this slows things down, I'll turn off the video, but I think it might be kind of cool to have this. We'll see how sturdy the system is and whether or not it can actually handle that. A lot of it will probably depend on um, bandwidth where I'm at. So anyway, we've got remove K, that removes the entry. Size is empty. Size just simply returns the number of key value pairs in the system. And then isEmpty returns if it doesn't have anything in it. That returns true, obviously. Now, this question of iteration is probably maybe one of the more confusing parts about this slide. It says it returns entry set returns an iterable collection of entries in M. And the question is, well, what do you mean iterable? The thing about a map is that, like we'll see soon, the underlying structure can be complex. It can be implemented through like a hash system, for example, which we'll see in a little bit. That's the next set of slides. Or it can be implemented through maybe a priority queue or something else. Like the underlying structure isn't really all that important to the overlying upper level ADT. But at the end of the day, you want to be able to get back a bunch of entries, perhaps, in order to print them. Like, let's say you've got your phone book or you've got your whatever, you've got your list of employee records. You might want to do some auditing and print all of those employees. Well, you've got this system that gives you a key value, but you need to be able to print all of them. So we have this concept of iterable collections being like lists, for example. So that'd be a list that would have an iterator attached to it that would start at the beginning of the ADT at like the first entry and go to the last entry. And you might have that for both the keys and the values. And that's why you see a different one there for key set and for values. So, taking a look at an example of this, we've got isEmpty on the initial map, which would return an empty set there. But now we're saying we want to put 5 and A into it. So the map ends up with 5 and A. We put 7 and B. So the map, now notice that 7 and B comes in there behind the 5 and A, but that doesn't really matter to the map user. That might as well have come in ahead of the 5 and the A, because the key thing is that in a map you use the value to get out, or the key to get out that value. So you would use the 7 to get out the B and the 5 to get out the A. You put in 2 and C, you put in 8 and D, so we're really just populating it here. Now, interestingly, if we do a put again on 2 and E, the output we're going to get from that is C, and it's not going to put 2 and E in. And that's going to be different to the multi-map, which you'll see a little bit later. But if we do a get in 7 on it, we get our output as B. We do a get in 4. Well, no one put the key in as 4. No one put that key in, so we're getting back null. Here you can see that we do a get on 2 and we get back E. Call size on it, we get 4. Remove on it actually gives you back the value that was stored in 5. Remove on 2 gives you back the value that was stored in 2. So as long as you understand these basic operations here, you should be good to go on the map ADT. So maps, as I said, are implemented in a variety of ways. In the STL, actually, within C++, they operate more like a hash. But you don't have to do that. Here's a list-based map where it's implemented as an unsorted linked list, basically. It stores the items of the map in a list, kind of like a doubly linked list, and this is just stored in an arbitrary order, so we're just sticking 9C, 6C, 5C, 8C, all in the list. And we've got a header that goes to the first node in that list. And then from there, we just go to each subsequent node, and each subsequent node can go to back to each previous entry, so just a standard doubly linked list. Now, of course, what you're probably thinking is, well, okay, do a doubly linked list, but the performance time on that is not going to be great. If we're looking for 8 as, for example, as a key, we have to go through all n nodes to get to 8. 8 is the last one, so we've got an O of n operation there. and that's problematic. And that's in fact what the getK algorithm does on a doubly linked list situation, as you can see here. We call getK. It has its positions, and we say, well, next, get the next one. If the key is equal to the key you're looking for, which is k, then return that value. Otherwise, return null. So it's literally a linear search for this key. Now that's almost the best we can do for now. I mean, we saw with priority heaps, you can do a little better. We're going to see hash maps in a little bit. You can do a little better there too with map implementations. But this is probably this is the most naive of the implementations of the map. So the put algorithm basically just says, okay, we're gonna get back our iterable list. That's what positions does, and it says, well, B has next. P, which is our iterator, equals B dot next. Now, don't let this throw you here. P dot element dot get key equals K. P is an iterator. So an iterator is like a wrapper class that gives you a position of the thing inside of the data structure. So when you say p.element, what you're actually doing is you're unwrapping it. So you get back the actual position with the p, but then you get back the actual element with p.element. You actually get back the node. So that's what p.element, that's why they have that there. And then t equals p.element.getValue. And then we just do that's just getting us the value out. Now notice here that we're saying s.set p comma k comma v, so it's setting at that iterator position, k in the v, and then returning the old value. So that's essentially what we set out to do, because we should just return the old value from that. And actually, if you look at, let's go back to this example. Notice that we put 2 and E on at this stage, and it returns C. Well, 2 and E, even though 2 and E was what was put on, we already had a C here. The reason they do that, and then they stick 2E in here, even though C was already present, I probably should have clarified that a little bit earlier in this presentation. The reason they do that is that if you want to know that you haven't inserted a duplicate, you get back the existing key, or the existing value, I should say, and then you could do something with that. The client of this ADT could do something with that. So that's why we do an s.set on P of K and V. Now, if this isn't found in the doubly linked list, we just add the last one, add it to the last one, and then we increment the variable count. Remove K is pretty simple, so we just go through here, go through the iterators, look for the key. Once we find it, we remove it by calling s.remove on P, and then we say n equals n minus 1. So very straightforward removal. You're just going through the whole list. Again, it's an O of n operation, but that's what we've designed here. So as you can see, put is the nice operation. That takes O of 1 time. And that's why quite often maps are preferred, because if you're going to be doing some situation where you've got a lot of retrieval, like, obviously in the case of a phone lookup, in the case of web surfing, in the case of, like the example I used before, in the case of employee record searching, basically all three of our running examples today, you're going to be doing retrievals much more often than you're going to be doing insertions. So the fact that you can get an O of 1 operation time for your put is very good. But as we'll see, this unsorted implementation is really only effective for a small number of things in our map. because get and remove take O of n time, because you have to traverse that entire sequence. So that's why we're going to move on to sort of the next next topic here, which is hash tables. I'm going to pause. I'm going to pause the recording for 30 seconds to a minute here, and get a new recording going, and then we'll start up on hash tables and continue from there today. But before I go on, does anyone have any questions on maps, basic maps with the doubly linked list implementation? All right. Well, if you do, I'm going to leave you guys. You guys all have talk permission, so feel free to chat. Otherwise, I'm going to stop this recording, and we'll be right back and go into hash tables.